Hello everyone, I am Bhuwan Joshi. I work at Udaipur Solar Observatory Physical Research Laboratory, Udaipur. The title of my talk is Observations of Solar Transients and Their Signatures at Low Frequency Radio Emission by Udaipur Callisto. I would like to thank the organizers of this conference, Space Education and Research Foundation, for providing me this opportunity to present my work. Let me begin by briefly describing the term solar eruptive phenomena. Solar eruptive phenomena correspond to the various kinds of transient magnetic activities occurring in the solar atmosphere in the form of solar flares, prominence or filament eruptions, and coronal mass ejections. These phenomena take place in the localized region of solar atmosphere, and they all are associated with coronal magnetic fields. As you will see in the later part of my talk, these our phenomena are strongly coupled to each other. Before starting the discussion on solar eruptive phenomena, I would like to show you this interesting observations, which tells about the effect of solar eruptions in the interplanetary medium and subsequently to near Earth region. So we see here intense brightening on the sun somewhere here, and this intense brightening is essentially a flare emission. The flare is followed by the eruption of plasma and magnetic field, which travels into the interplanetary medium. And when these eruptions are directed towards the Earth, the CME will reach the Earth, and finally it will interact with the Earth's magnetosphere, and this creates auroral activity. So this animation shows in a very beautiful way the impact of solar activity in the near Earth region. So this is the propagation of CME, and finally the CME, that is the plasma and magnetic field, interacts with the Earth's magnetosphere, and this phenomena is also responsible for geomagnetic storms. Now let me begin with the details about solar flares. So a flare is essentially a transient magnetic explosion in the solar atmosphere. And in a large flare, the energy in excess of 10 to power 32 arcs is released, and this energy release occurs in the localized region of solar atmosphere. The time scale of solar flares vary from few minutes to several tens of minutes. So this is really a powerful explosion, and this explosion can be understood in terms of millions of 100 megaton hydrogen bombs exploding at the same time. Or we can say that this energy is 10 million times greater than the energy released from a volcanic explosion. So here I show you an animation of solar flares, and these images are taken in H-alpha from ground-based BBSO observatory. So what we see here is intense brightening in the chromosphere in a region which is close to the sunspots. The dark structures here are sunspots. So the energy release takes place close to the sunspots. We see several elongated bright structures here, which corresponds to the energy release. According to the topology involved, the flare can be classified into two categories. We have confined flares, we have eruptive flares. Confined flares lack coronal mass ejections, while the eruptive flares are associated with coronal mass ejections. So for a space weather perspective, the eruptive flares are extremely important. There is a universal consensus that only magnetic reconnection can power solar flares. So reconnection is a process which converts stored magnetic energy into the thermal and non-thermal energies. So we'll discuss about magnetic reconnection a few slides later. Now let me discuss the solar filaments. So here we have H-alpha image of the full sun, and in this H-alpha filtergram, we see several dark elongated structures. So these structures correspond to filaments. And when these structures appear near the limb of the sun, they appear bright and we term them as prominence. So essentially filaments and prominence are same structures. There is difference only in their geographical location or heliographic location, more correctly. So filaments are large magnetic structures which confine cool and dense plasma in the solar corona. The typical temperature of these structure is 10 to power 4 Kelvin, while the density is of the order of 10 to power 17 cubic meter. If you compare these values with the values in the ambient corona, then you find that the temperature of a prominence is about 2 order of magnitude less than the ambient temperature, while the density is about 2 order of magnitude higher than the typical coronal values at that height. Here we show the eruption of a prominence. You can see the dark structure in the beginning. The animation on your left shows filament eruption in H-alpha, while the animation on your right shows the eruption of same filament in 304 angstrom, and these images are taken from AIA onboard Solar Dynamics Observatory. So we see the eruption, first activation, and then the eruption of the whole filament structure, and this is followed by the intense brightening in the source region, which you can see here in H-alpha as well as in 304 angstrom. And this brightening corresponds to solar flare. And when these structures are able to escape the sun successfully, they form a part of coronal mass ejection. Here is another interesting example of a prominence eruption, which is occurring near the limb of the sun. So we see several activities in the corona, and during these activities, we see the activation of a filament which finally erupts. And the eruption of the filament is associated with intense brightening in the source region, which corresponds to the flare emission. The plot on your right compares the height time plot of a prominence with the intensity of the flaring region. The red curve here shows the flare time profile in soft X-rays, while the plot here in asterisk symbol, it shows the height time of the corresponding prominence eruption. So we see that both the processes are synchronized with each other. In the beginning, we have slow evolution in the flare emission. At this time, the filament also activates slowly, while the impulsive phase of the flare results into the rapid expansion and subsequent eruption of the filament. So here we discuss the coronal mass ejections. The animation on your right shows white light images of the solar corona taken from LASCO onboard SOHO satellite. So we see here the eruption of a huge bubble-like structures, bright bubble-like structure, and the eruption of this large-scale structure correspond to a coronal mass ejection. So the coronal mass ejections essentially consist of large structures containing plasma and magnetic field that are expelled from the sun into the heliosphere. Here we give physical parameters of coronal mass ejections. So there is a large variation in the speed, mass, kinetic energy, and angular width of these events. Especially, we see very narrow coronal mass ejections, we see very wide coronal mass ejection, and when the width or the angular width of a coronal mass ejection is about 360 degrees, then we call such ejections as halo CMEs. And these CMEs are essentially earth directed, and in many cases, they create geomagnetic storms. So the decades of observations have taught us that a typical CME has a bright front loop, which is followed by the dark region here, which we call as cavity. And finally, we have a bright structure, which is the core. So the core essentially corresponds to the prominence eruption. The typical three-part model of a CME shows a nice correlation between CME, prominence eruption, and the flare eruption. So in the beginning, we have a prominence here. The prominence is constrained by overlying magnetic field lines. When this prominence activates due to some kind of instabilities, it stretches the overlying field lines, and this creates environment for the magnetic reconnection. Once the magnetic reconnection sets in underneath the erupting prominence, we see intense flare emission, which creates emission from the coronal loops as well as from the foot point of those loops. When the prominence escapes the sun successfully, it becomes a part of the coronal mass ejection. So the classical three-part CME structure couples all these processes. It couples CME with prominence eruptions and finally the flare which occurs in the solar source region. So basically all these processes are coupled with each other, and magnetic reconnection plays a very important role in triggering these processes. Here we have a schematic plot which shows the relation between the CME speed and the intensity of flaring emission. The red curve here represents the flare emission in soft X-rays, while the blue curve here shows the kinematic evolution of CME by calculating the speed of the CME. So what we find is that the beginning of the CME, the initiation phase of the CME corresponds to the pre-flare enhancement, while the acceleration phase of the CME corresponds to the rise phase of the flare. After the flare maximum, CME propagates outward into the corona and interplanetary medium, and at this time, the flare undergoes the decay phase. So the temporal coincidence between CME acceleration and flare flux represents CME eruption is strongly coupled with the magnetic reconnection process that causes the flare. Here we show an animation to discuss the magnetic reconnection in a simplistic way. The cross inside the circle, this region represents the polarity inversion line or the neutral line. So we have magnetic fields of one polarity, one side of it, while we have magnetic field lines of the opposite polarity on the other side of it. The inward yellow arrows represents the inflow. With the plasma inflow, the magnetic field lines are also brought close to each other. They reconnect at the neutral line, and this is followed by the outward flows. And we have the new rearrangement in the magnetic field structure. So the magnetic reconnection is a breaking and topological rearrangements of oppositely directed magnetic field lines in the plasma. And this powerful process is the backbone of solar eruption, because it can convert the stores magnetic energy into the plasma, kinetic, and thermal energy. Here we represent different phases of a flare evolution by showing the schematic time profiles in different wavelengths. So from top to bottom, we have flare light curves in microwave, then in H alpha, then in extreme ultraviolet, soft X-rays of intermediate energy, that is 10 to 30 keV. Then we have hard X-ray light curve at high energies greater than 30 keV. So what we find that the flare evolution in different wavelength has similarities as well as differences. So essentially, the evolution of a flare depends upon the wavelength in which we are observing the event. So this shows that flare is essentially a multi-wavelength phenomena, and if we want to probe the physical processes happening at different regions of solar corona during the flaring process, we must analyze multi-wavelength observations. So the time profile also shows that we have a pre-flare phase, which is shown by the small increase in the intensity in soft X-rays and extreme ultraviolet. Then we have an impulsive phase, which lasts from few seconds to tens of minutes, and energy release occur in the form of X-ray, EUV, and microwave emission during this impulsive phase. Finally, we have the decay phase, and the decay phase is dominated by the thermal emission in soft X-ray and in H alpha. After the impulsive phase, we see that the soft X-ray emission, which we show here, or in fact in H alpha also, we see a very gradual decay in the flare brightness. And this corresponds to a prolonged decay phase. And this prolonged decay phase is very much extended in the eruptive flares, that is the flares which are associated with coronal mass ejections. Here we show an animation of an interesting X-class flare. X-class flare means a flare of very high energy. And this is actually a typical standard flare, because in this event, we see two kind of X-ray sources. We see low energy X-ray source and two high energy X-ray sources. The low energy X-ray source, which we show by white contours, represent emission in 6 to 12 keV, while the black contours here represent emission in 50 to 100 keV. So from these zoomed images, it becomes clear that the low energy emission, which also moves upward as the flare progresses, corresponds to the emission from the top of the flaring loops, while the conjugate foot point sources occur close to the foot point locations of the flaring loops. So this is what we expect in a typical solar flare. When the events are occurring close to the center of the sun, we see the foot point emission, that is the emission from the foot point locations of the overlying coronal loops in terms of flare ribbons. So flare ribbons are historically observed in H alpha. They can also be observed in UV or in chromospheric EUV channels like 304 angstrom. An important property of the flare ribbon is that the two flare ribbons, they occur on the opposite magnetic polarities. So in this panel, the red contours represent one kind of polarity, while blue contours represent the polarity opposite to that. So this is expected because the two flare ribbons, they essentially join the foot points of a flare loop. So they must occur on the opposite side of the magnetic neutral line. So the evolution of flare ribbon and the location of hard X-ray sources are shown in these zoomed images. The evolution of loop top and foot point sources becomes very clear from this animation. So we see the low energy soft X-ray emission from the corona, because it is a limb flare, and this is followed by the development of flare ribbons, and in the impulsive phase we see hard X-ray sources which lie over the two flare ribbons. The important characteristics of a major eruptive flares are summarized here. We see the formation of flare ribbons, and with the formation of flare ribbon, we have the growth of the flaring loop. And in the decay phase, we see that the whole flaring region is enveloped by large post-flare loop arcade. The important thing is that the Doppler shift measurements show that the apparent motion of the post-flare loops and corresponding ribbons are not caused by mass motions of the plasma. So it means that the growth which we see in the formation of flare ribbon is essentially an apparent growth, an apparent motion. So we have the formation of newer coronal loops as the magnetic reconnection site moves upward into the solar corona. Here we summarize the important questions in the contemporary solar physics in the area of flares and coronal mass ejections. The most important question is about the magnetic configuration in the pre-eruption region, which can store huge amount of magnetic energies. Once we have triggering of an event, the question comes, what fraction of energy released in flares goes into acceleration of electron, and what fraction goes into the heating? Whether we can image the acceleration region from direct observations, this is another important question. What is the exact process of heating and particle acceleration? From a space weather point of view, we would like to know the mechanism of CME initiation and evolution in the corona and interplanetary medium. So these questions, they form the basis of our research in contemporary physics or contemporary solar physics as far as the eruptive phenomena on the sun are concerned. Here we show the basic process that happened during a flare. As we discussed earlier, we have a flaring loop here. One foot point of the flaring loop has one kind of polarity, while the other foot point has another kind of magnetic polarity. The reconnection region is somewhere here in the corona. The reconnection will release lot of energy, and this energy goes into the particle acceleration as well as heating of the plasma. The accelerated particles, they will move upward as well as the downward direction. The downward moving electrons will be guided by these magnetic field lines, and finally they will reach the foot point location where the density is higher, and therefore they will be collisionally stopped by the denser plasma here, and this creates non-thermal brahmastar lung, which is responsible for high energy hard X-ray emission from the foot point locations. At the same time, the same electrons which are coming toward the foot point location, when they will gyrate along the magnetic field line, they will create microwave emission. So we have a multi-wavelength view of the flare in which different emissions are generated by different mechanisms, but they all are coming simultaneously. So we need multi-wavelength observations to probe the energy release process completely. Here is a model of solar flare given by Shibata, which is also called unified model. So in this model, we have a flux rope. The flux rope can be seen as a plasmoid or as a filament in the observations. The upward movement of the plasmoid or filament creates a density depletion, and this produces reconnection here, and then we see a diverse variety of multi-wavelength phenomena. I would like to emphasize this important discovery, which is the discovery of above the loop top source. And this discovery was done by the observations from Japanese satellite Yoko. So in this 1994 paper, Masuda et al. Reported for the first time the appearance of a hard X-ray source from the coronal region, besides two foot point sources at the location of the foot point of the flaring loops. So the discovery of the hard X-ray coronal source was a major breakthrough in the localization of particle acceleration near the magnetic reconnection site. And this observation immediately supported the flare models involving magnetic reconnection in solar corona. In case of limb event, if the circumstances are favorable, then we can observe the high energy loop top emission. And when we do the imaging analysis with the hard X-ray spectroscopy, then we have an opportunity to characterize the nature of emission. We can also calculate thermal parameters like temperature and emission measure of the flaring region. And from the power law component, we can calculate the parameters such as non-thermal energy contribution of the flare. The role of magnetic reconnection is extremely important, and the simulations also show that the reconnection can also generate a flux row after the onset of a flare. So here we saw the reconnection onset, and this is followed by the generation of this red colored structure, which is the flux row. And then with the progression of simulation, this structure ascends. So this is in agreement with the standard model of solar flares. So the magnetic flux ropes can emerge from the solar convection zone or from the subphotospheric layers, but at the same time, they can be created in the corona during the magnetic reconnection process. Now let us come to the radio observations of flare CME events. We would like to discuss here the solar dynamic radio spectrum. A typical dynamic spectrum is shown here. So the dynamic spectrum is essentially a plot between the time and the frequency, and the color code here represent the intensity level at different frequencies. So when we have this kind of dynamic spectrum, then during flares or CMEs, we see different structures in it. So these different structures have been classified as type 1 structures, type 2 structures, type 3 structures, type 4 structures, and type 5 structures. Here I would like to briefly discuss about type 2, type 3, and type 4 structures. The type 2 structure, which is shown here by this red color, shows a frequency drift. And this essentially corresponds to shock waves, the propagation of shocks, which are generated by the coronal mass ejections. On the other hand, this type 3 structure show very fast frequency drift. These are almost vertical structures. They show very fast frequency drift, and they are attributed to the escape of energetic electrons from the reconnection region. The type 5 structures are similar to type 3 structures, but in this case, the drift rate is slower. There are type four structures as well, as we see here by this orange color code. And these structures represent stationary burst or the burst which move slowly. And these are due to the electrons trapped in moving or stationary magnetic structures. So these type 4 structures are a kind of continuum which show very small or no movement. Now let us see a real radiodynamic spectrum from 50 to 500 megahertz, and in x-axis we have time. So this corresponds to a large X-class flare. The flare time profile is shown by the white plot here. So what we see is that during the early phase of the flare evolution, we see vertical structures which show the onset of magnetic reconnection. And these vertical structures are type 3 radio bursts. During the rise phase, we see this drifting structures, these bright drifting structures, which we call as type 2 structures. And these structures are attributed to the evolution of coronal mass ejection and generation of shock by the CME propagation. So essentially, the first coronal mass ejection, they create shock, which in turn generate type 2 radio structures. Now let us come to low frequencies. So this is a dynamic radio spectrum obtained from wind waves satellite. So here we see type 3 structure, type 2 structures, and this type 2 structure also shows enhancement of emission in the form of multiple patches. So these radio signatures are extremely important. They tell about the onset of flare emission. They tell about the accelerated particles which are ejected from the reconnection region. And finally, they tell about the propagation of CME and also the interaction of one CME with the other CME. In this plot, we show high time evolution of several CMEs. So by comparing the high time plot of CMEs taken from white light observations with radio spectrum, we can address different physical processes that occur during the flare CME event. In order to understand the CME propagation and the particle acceleration during the flaring process, we have installed a Callisto solar radio spectrum at Udaipur Solar Observatory campus of Physical Research Laboratory in Udaipur, and this instrument was commissioned in October 2018. So this is a relatively simple instrument. The main part of this setup is an antenna. So we are using a simple log periodic dipole antenna of about 4 meter length. It receives radio signals from the sun. Then we have a low noise amplifier over here. And this low noise amplifier amplifies the signals, and then the signals enter into the solar radio spectrum, the Callisto spectrum. And finally, inside this hut, we have a computer which stores the radio signals, and also it analyzes the radio signals. The Callisto stands for Compound Astronomical Low Cost Low Frequency Instrument for Spectroscopy and Transportable Observatory. The importance of this instrument is that it's a portable instrument and it's a low cost instrument. But the beauty is that it gives real time monitoring of the flare CME events. And therefore, it is a very important equipment for space weather purposes. Here we show various subsystems of Udaipur Callisto spectrograph. This is the log periodic dipole antenna. And in panel C, we show the Callisto spectrometer. And finally, we have a computer which stores the data. Here, we show the specifications of our antenna, the log periodic dipole antenna. Its length is about 4 meters. It has 28 elements, and each element vary in length and width. The instrument became operational in October 2018, and since then, we are having regular monitoring of solar activity by Udaipur Callisto. The details of this instrument can be found from our website. Here we show an important observations taken from Udaipur Callisto during a very small flare of C class. So we see that it's a C class event, C1 class event, but it's a long duration event. And this flare shows two phases, stage S1 and stage S2. So in these goose profiles, the two stages are clearly seen. During the stage 2, we saw radio emission here. And when we analyzed this data in detail, then we found that this radio emission corresponds to a type 4 radio burst. And using suitable coronal density models, we can also estimate the height at which the emission is originated. So using such model, we estimated that the height corresponding to this emission is from 1.1 solar radii to 1.5 solar radii. We analyzed this spectrum in detail. We split the spectrum in two frequency bands, low frequency band and high frequency band. And when we did cross correlation study, then we found that there is essentially no drift between low frequency band emission and high frequency band emission. So it means that it's a type 4 burst, and the structure of the burst suggests that this type 4 burst is stationary in nature. So it means that this burst represents emission from the electrons which are trapped inside the flaring loops. Here we show another interesting observations from Udaipur Callisto, and we compare these observations with the low radio frequency observations from wind wave satellite. We see several type 3 structures which represents the ejection of accelerated electrons from the flaring site, and the extension of this structure in low radio frequencies suggests that these electron beams could successfully pass through the overlying coronal layers, and finally they reach the interplanetary medium. So let me show one more observations from Callisto spectrometer, but this observation is not from Udaipur. It is from Greenland Callisto system. This flare is an X 9.3 flare, which occurred on 6 September 2017. So these observations are about 1 year before the commencement of Callisto at Udaipur Solar Observatory. So we have worked extensively on this event, and this event I'm showing here because this was the largest flare of solar cycle 24. So in radio, we clearly see intense type 3 emission, which is followed by type 2 structure. So the type 3 emission corresponds to the reconnection process, while this type 2 emission suggests the formation of shock by the outward propagating coronal mass ejection. So let me complete my talk here with a few concluding remarks. In contemporary solar physics, we should have a kind of synergy between multi-wavelength observations with magnetic field measurements, extrapolations, and simulation, because this approach is the key toward a better understanding of various reconnection driven transient processes in solar atmosphere. We also highlighted the importance of analyzing uh, the observations of dynamic radio spectrum as they provide important insights on the initiation and evolution of flare CME events, CME propagation characteristics, and the properties of CME-CME interactions. The low radio frequency observations from Callisto at USOPRL are extremely important in understanding the physics of flare CME processes. Besides, it is also important for the real-time monitoring of solar eruptions. So with this, I would like to end my talk. Thank you very much.